So in the first example of finding an exponential model, we have a situation where some turtles are released into a wetland. We're going to call that time t equals 0. 4 years later, the biologist goes back and estimates that there are about 300 turtles. And then 3 years after that, they go back again and they estimate that there are about 450 total turtles. So in part A, you said assuming the population grows exponentially, at least in the short term, it will be exponential, but we know that this will be logistic because of population growth can't be infinite. But assuming it grows exponentially, let's find a model for the population at time t. And then in part B, we're going to use that model to see how many turtles would there be there after 12 years, and then at what rate is the population changing after 12 years. Okay, so in part A, I really like pictures, graphs, and I really like connecting the two together. So I mean, we know that the model, since it says exponential, we're going to have a model that looks like this. Y equals CE to the KT. And the thing is that we need to find C and K. It's kind of like when we have Y equals MX plus B and we need to find M and B. It's the same kind of idea. Okay, E is just E and T is the input variable. So C and K are going to be numbers that we need to find. We're going to use our data points that we have here in order to determine these. Okay, so if we were to just kind of draw a picture, when we've got years here, and then we've got population on the y-axis. Okay, so this is the variable t, and this is the variable y. We actually know a couple things. We know we don't know how many were released in the beginning, but we do know that after 4 years, we've got a total of 300 turtles. So maybe we could make, we'll plot some points here, but we can also make a chart. So t and y. So we don't know at 0, but we do know that 3 years after the initial release, we have 300. And then 4 years, or wait, oh, sorry, 4 years after that. I got the numbers confused. So 4 years, sorry about that, 4 years later from the beginning, so when t equals 4, we have 300. Okay, then 3 years after that, so 7 total years from the beginning, we've got 450. Okay, so let's plot these points here. So this point would be 4, 300, and this point would be 7, 450. Okay, so we'll do 1, 2, 3, 4, 5, 6, 7. And then we've got some population here that goes up to, I don't know, maybe I'll go up to like 600 here. So here's 600, here's 300, here's 450, here's 150. So the points that we know that are on the graph are 4, 300. So there's that point. And then 7, 450. So there's that point. We know it's growing exponentially, so it's probably going to look something like this if we were to graph it. And we want to figure out, what is the formula for this? It's going to look like this format. So there are a few ways that you can go about this. Here is my suggested way, but there are other ways if you know one or if you find about one that you like better. The first thing to do is to plug in both points. Plug into the, this formula here, plug in these points. Okay, so that's going to look like, try to put them in the right spot. So we've got 300 is y, and then that's when t is 4. And then we've got 450 is y, that's when t is 7. And I'm just going to write this a little bit better. I don't like that k times 4. I'm just going to write that as 4k. And I don't like that k times 7. I'm just going to write that as 7k. Okay, now we have two equations, and we have two things that we want to solve for. The way that I suggest going about this is by kind of like an elimination type thing. So I'm going to label these equations here. It's 1 and 2. So what I suggest you do is we take one of the equations and solve it for C. So I'm just going to take the first one and I'm going to solve it for C, but it doesn't matter which one you want to do. So I'm going to do 300 equals CE to the 4K. So if I solve this for C, I'm just going to divide by e to the 4K. Now another way that I could write this is 300e to the negative 4K, and I think that would probably be better. Now what I'm going to do with this is I'm going to put it into the other equation. I'm going to take this and I'm going to put it in for C into here. Why? Because then I'll get rid of the C and we'll be able to solve for K. Okay, so then we want to substitute this into, I think I had too many things, or substitute into the other equation. Substitute this into the other equation. So now I'm going to be using equation that I numbered 2. Okay, and I'm going to put in that value for C into this equation. So we've got, so I'm looking here now, so we've got 450. And instead of C, I'm going to write 300e to the negative 4K. And then that's times e to the 7K. In order to solve for K here, we just got to do a little bit of, algebra-ing. But that's going to be our goal. So we're going to solve this for K. So I see some like bases here that I'm going to combine together. So we can add the exponents. Negative 4K plus 7K is positive 3K. Okay, now I want to solve for K here. We want to get the numerical value for K. So let's divide by 300. Um, 450 divided by 300 is 1.5. Now remember to solve an exponential equation that is, you're looking to solve for something in the exponent. We want to apply the natural log or take the natural log of both sides. So that's going to cancel out the e's. We'll have natural log of 1.5 equals 3K. Now to solve for K, we're just going to divide by 3, divide by 3. And so what that tells us is that K is equal to the natural log of 1.5 over 3. Now it's okay to get a decimal place for this, or a decimal approximation for this if you'd like. But this is the exact value, so you can also leave it this way. But if you are going to get an exact, a non-exact value, an approximation for this, then you should go out as many decimal places as you can, or as many decimal places as your calculator tells you. So if you type in the natural log of 1.5 and divide that all by 3, you get 0.135155036. So you want to keep all of these, unless you just want to leave it as the exact value with the natural log. Okay, so let's just take stock of what we're doing here. So we just found the K. So we found the K, but we still need to find C. We did 90% of the work already. To find C, we already have this neat little formula for C in terms of K. Right? If we just plug in here the value for K we got, then we'll be able to solve for C pretty easily. Okay, so the last thing we want to do here in order to find our model is find C. Right, so we had that C was equal to 300e to the negative 4K. So I'm just going to plug in that value for K, whether it's the approximation or it's the exact value. They'll be pretty close. Okay, so when you do this, we will get approximately 174.7 V2. Okay, now this is the initial value. C represents the initial value. So this is the, at the beginning, when they released these turtles into the wild, they released about 175 of them, according to this model. Okay, so remember, in the end, like we want to build this model. That's what we're looking for, right? So it's going to be y equals c e to the kt. I'm actually being kind of bad here. We should probably leave this as an exact value instead of rounding it to all these decimals, but that's okay. So what I'm saying here is actually this probably not that great to have that. What we should probably do is say that this is more exactly the natural log of 1.5 over 3. All of that is times t in the exponent. It's probably the better way to do that. I'm just thinking of in your web assigned questions how they really like exact numbers. So you might want to stick with this. But for me, I don't really mind. Either one is good. Okay, so here's the model. N times t, you can find the population by plugging it into this formula. So we've got some other questions here, and I'm just going to, so that's part A, I'm just going to make this smaller so that forever running out of space. Okay, that's why I like this, because I can just kind of shrink stuff and move it around. I'm teaching on the board, I almost in my mind wants to do that. Like, that doesn't make sense. Anyway, in part B, we want to know how many turtles are there after 12 years and at what rate is the population changing after 12 years? Okay, so now we found this formula. It's actually relatively straightforward to answer these questions. So for part B, we want to know the population at 12 years. So in other words, at t equals 12. So we're just going to plug in a 12 for t. And just take some care when you're plugging this in to your calculator. I know it looks like all of this is in the exponent. So just, really be careful with doing that. And I'm going to do this with you too. So let's do 174.72 times e to the parentheses, natural log of 1.5 divided by 3, and that's times 12. We should get about 884.5. So we could just round that to, how about 885 turtles? 885 turtles. And just to give you some, like if you were to actually leave this as an approximation with all of the decimals there, you get the exact same answer for this, or at least very close to the hundredths place. So, either way, again, you want to do that is fine. Okay, the other part of part B says at what rate is the population changing after 12 years? So we call this rate of change at t equals 12. You remember in calculus, huge idea, rate of change is the derivative. So we need to find y prime. Okay, so we're going to differentiate this function. It looks very complicated, but it is overall an exponential function. This number here is a constant multiple in the front, so that's just going to stay there. And in fact, when we differentiate e to anything, it stays there. So we're just going to get itself out. But then we're going to multiply this by the derivative of the exponent. Now remember that this whole thing here times the t is basically this number. So when we find the derivative of the exponent, it's just going to be this number, or more specifically, that number, the natural log of 1.5 over 3. Okay, so this all is going to get multiplied by the natural log of 1.5 over 3. Or again, 0.13515536. That's what this number is here. You know, I want to plug in 12 because we want the rate of change at 12 years. So I'll just plug in a 12 for t. Oh, these are so complicated. So we've got that all in the exponent, and this is all times the natural log of 1.5 over 3. So again, carefully plug this into your calculator. Make sure that you are comfortable evaluating something like this. And let's see, I'll do it too. So we want to do times the natural log of 1.5 over 3. And you should get 119.5. So we'll say this is approximately 120 turtles. This is a rate, so turtles per year. Okay, so what this means is that in year 12, the population will grow because we have a positive rate of change by approximately 120 turtles. Right? Only in year 12, that's what this is an approximation for, the growth. So from 885, you will gain 120 approximately in that year. Growing very quickly, lots of turtles to reproduce. Okay, so here is an example with how to find an exponential model. In the next example, we will do this again and also find another rate of change, but it will be in a slightly different context. So tune into that and I'll see you then.